Welcome. This is a video presentation of the paper A Universe from Itself, the Geometric Mean Expansion of Space and the Creation of Quanta, Part 8, Significant Geometric Means Associated with the Small Energy Quanta and the Small Radius Quanta. Part A, the size of the whole universe. Part B, the particle radius. We saw in Part 6 that the geometric mean counterpart to the radius of the hyperverse is the small radius. We get this by multiplying the radius of the hyperverse times the small radius, and that quantity will equal the initial radius squared. Rearranging r sub s, small radius, is this term here. And we want to know what is the volume taken up by the small radius, and that comes to 2 pi squared times the small radius cubed. To find out how many small radius quantum volumes are in the observable universe, we'll divide V sub O, the volume of the observable universe, by the small radius quantum volume, V sub S, and we get a number, and that number happens to be r sub h over 2LP to the 6th power. It's the cube of the large number. We'll divide the energy of the observable universe by our number to get the energy value associated with a small radius quantum. We will now use the energy associated with small radius quantum in a geometric mean relationship, where the energy of the SRQ times some unknown energy, of course this is where we're going, it's going to be the energy of the whole universe, is equal to the initial energy squared. And we find that this energy value is equal to this ratio. So we'll start plugging in our numbers. We have the energy value that we're looking for is equal to the initial energy squared divided by the energy of the SRQ, which is a very small energy. And it works out to be this value times this, which comes to the energy of the observable universe, times this particular factor, the large number squared, r sub h, divided by 2LP to the 4th power. And so the geometric mean counterpart of the small radius quantum energy is an enormous energy, which we will claim is the energy of the entire universe, the whole universe. Not just the observable, but that which is beyond it. It's the whole thing is equal to the energy of the observable universe times our multiplication factor. Numerically, the whole universe is larger than the observable universe by a factor of more than 4 times 10 to the 243rd power. And here we're going to calculate the radius of the whole hyperverse. Knowing that the energy density is identical throughout the universe, we can therefore assume that the volume of the whole is equal to the volume of the observable by the same multiplication factor. The surface volume, 2 pi squared times the radius of the whole cubed, would therefore equal to this volume. And we work out the radius of the whole hyperverse to be the radius of the observable times r sub h over 2 times the Planck length to the 4/3 power. We'll take our radius that we just calculated for the whole hyperverse and again insert into a geometric mean relationship, which should make this sense because it started at the same time the whole universe did. So the whole radius times what we're going to call the small whole would be equal to the initial radius squared. And we work it out. We find a very small radius, r sub h times 2 Planck lengths divided by r sub h to the 10⁻³ power, and that comes to about 2.4 times 10 to the minus 177 meters. This ultra small radius is not a random value, but will show up again as the smallest radius possible in the hyperverse model. It will prove to be the radius of the collapsed small radius quantum that forms particles of matter, a topic in the paper on the origin of matter. We're going to switch over now to the small energy quantum energy. We saw in the discussion of the creation of quanta that the geometric mean of the energy of the hyperverse was the small energy quantum, E sub SEQ. And we know that that small energy quantum energy is equal to the initial energy squared divided by the energy of the observable universe. And it works out, as we've seen, to C times h bar over the radius of the hyperverse. And if we divide the energy of the observable universe by the energy of the SEQ, we can find out how many SEQ units there are in the observable universe. So the energy of the observable universe divided by the energy of the small energy quantum gives us a number, and that works out to be the large number. And now we're trying to calculate the radius of small energy quantum. So again, we'll take the volume of the observable universe and divide it by how many small energy quantum units are in it, and we get a volume of 2 pi squared times this unit here. And this is the radius cubed, so we'll just take the cube root of this number here, and we'll find that the radius of the small energy quantum is equal to r sub h times 4 times the Planck length squared to the 1/3 power. Here we take our small energy quantum radius, insert it into a geometric mean relationship. So we multiply the small energy quantum radius times some unknown radius, and it will equal the initial radius squared. Rearranging, we find this unknown radius to be equal to this value here, which is 16 times the 4th power of the Planck length divided by the radius of the hyperverse and the quantity to the 1/3 power. And we'll work out the value for our unknown radius here. And it comes to approximately 1.6 times 10 to the minus 55 meters. And we're going to make the claim that the radius that we just determined is the particle radius, the ideal particle radius. The paper on the origin of matter, the next paper in the series, will go into great detail in discussing why this is the case. So we've seen that the small radius quantum radius gives us the small radius quantum energy, whose geometric mean counterpart is the energy of the whole universe. And the small energy quantum energy gives us the small energy quantum radius, whose geometric mean counterpart is the particle radius. Both of these topics, the energy of the whole universe and the particle radius, are dealt with in detail in other papers.